The paper that I present in this video deals with the joint effects of infection risk at work during the COVID-19 pandemic and automatability of different occupations on employment within these occupations. The paper was written jointly with Anna Abeljansky and with Roman Stöllinger. In terms of the background, we start with the observation that production processes 100 years ago were very different from production processes nowadays. We see here a picture of a car factory from about 100 years ago, and we see that this conforms very well to how economists model production processes at the aggregate level in the form of the Cobb-Douglas production function. So we have two production factors, human workers and physical capital in the form of this assembly line, and there is a complementarity between the two. So without any workers, you cannot produce any output. Without physical capital, you cannot produce output. You need both of them in order to produce. If you Google modern car factory, however, then what you are likely to get is a picture like this one here, where you don't have any workers on many production steps. Instead, you have two different types of capital. Physical capital in the form of this assembly line, as in the previous picture, but then also physical capital that assumes the role of labor in the form of these industrial robots. So for the first time, actually in history, it becomes possible that the production factor physical capital on its own produces output, and you can fully substitute workers away by the use of physical capital. As you can imagine, this has strong consequences on economic outcomes such as economic growth, productivity growth, unemployment and inequality. For example, if you build in a production function where you can perfectly substitute human workers by physical capital, if you build this into a solo growth model, you get perpetual economic growth even without technological progress, and you get a declining labor income share as it was observed over the last decades, which you do not get in the standard solo model. This graph now depicts the number of industrial robots worldwide that were in operation. It starts in the 1970s. The stock is compiled by the International Federation of Robotics. And we observe that indeed automation in this form of industrial robots is a rather new phenomenon. So the first industrial robot was used in the 1960s, but throughout the 1970s and 1980s, adoption was still rather sluggish. Only in the late 1980s and 1990s, we had some growth. But the real takeoff occurred after the global financial and economic crisis, where since then we have observed growth rates of the stock of operative robots at the order of 15% per year, which is of course higher than growth of any workforce in any country, and growth of per capita GDP, which really hints towards automation being intensified, so that there is an intensification of robot use in economies all around the world. Now, one thing to keep in mind is that industrial robots are only one form of automation. And indeed, it's the form of automation where we have most data on it. So academic papers of the last decade or so mainly used the data of the International Federation of Robotics on the number of industrial robots worldwide to come up with estimates on the effects of robots and so on. However, there are also other forms of automation. One particularly important one is 3D printing or additive manufacturing, which is quite well suited to automate customized production. So industrial robots are very useful in routine tasks and in mass production, but 3D printers can also automate customized production. For example, the hearing aid industry relies a lot on 3D printers. And there, every hearing aid is basically fit to the patient's ear. So every hearing aid is different. And before that, this involved a lot of labor input. But nowadays, you can send a scanned file of the ear to a 3D printer and then print the hearing aid. Autonomous driving is also mentioned here on this slide because it's so important. It affects so many workers. So taxi drivers and truck drivers, that's a very large group actually. And if we see in the future true automation of driving, then we can be sure that this will have strong effects on the underlying economic structure. And over the last few months, so this is recorded in at the beginning of 2024, we've seen a lot of progress in machine learning and AI. So ChatGPT, as it was introduced in late 2022, has made a lot of headlines, and we know that some things like diagnosing diseases, which is essentially a pattern recognition exercise, is done much better by algorithms than by doctors, particularly for rare diseases that doctors see only infrequently or never at all. Writing reports, news flashes, ads, and so on, that's done by AI already, and even doing science, so in drug development and so on. And there was even a paper published in Science, I think in 2009, that where they gave an algorithm just the data of a swinging coupled pendulum, and the algorithm was able to recover Newton's laws of motion out of that. So these are all different forms of automation, and we should keep in mind that there are these different forms, but typically we only have data on industrial robots and this associated automation of mass production of routine tasks. I've already said that the consequences of automation have received a lot of attention in the literature over the last years. So the effects of automation on economic growth, productivity growth, the effects of automation on inequality in wages, but also inequality in terms of the functional income distribution. So the shift away from income from the production factor of workers towards the production factor of capital, the effects of automation on unemployment, and so on and so forth. But what has received a little bit less attention is the question what the causes of automation are. But I mean, technological change is an obvious one that has received a lot of attention by the papers by Fry and Osborne and Arns and co-authors that essentially address the extent to which certain tasks can be automated from a technological perspective. But then, of course, technological automatability does not imply that a firm indeed automates production in reality, because there are also economic considerations play a role. What has been shown is that, of course, high wages provide an incentive for firms to invest in automation, because then it can save more on the wage bill. Labor market tightness, of course, if there are not enough workers in the economy, I mean, that would lead to higher wages as well. But if you cannot find workers, then this is also an incentive to automate. And particularly demographic change has been shown to play a very important role, because if you have a decrease in fertility, for example, you can imagine that a little bit later workforce growth decreases quite strongly. And of course, this provides another incentive for automation. The effects of demographic change can also be illustrated quite well by such a world map that depicts automation density across different countries. So that's the number of industrial robots per 1,000 manufacturing workers. And here it is the case that the darker the color of a country is, so the darker the blue is here, the higher is the automation density. And the lighter the color of a country is, the lower is the automation density. And the countries that are depicted in white, they have no data, but basically that's almost synonymous with having a low number of industrial robots or no industrial robots at all. Now, what we observe is that particularly those countries that are aging fastest and have the lowest fertility rates have the highest robot densities, such as South Korea, Japan, Germany, Italy. And we have a lower automation density in countries that are not aging so fast, such as the United States, France, and the UK. United States and France have higher fertility rates than other countries, and also the United States has more immigration. The United Kingdom had a lot of immigration from Eastern European countries over the past decades. There is also perhaps because of that, no labor market shortages, and so on. So on average, what we see is countries that suffer more from demographic challenges, they use more industrial robots on average. In this paper, however, we are interested in a different causal effect of automation, where we want to ask ourselves whether there is a role for transmissible diseases in this context, particularly in relation to a pandemic such as COVID-19. And the intuition behind that is simply that robots cannot be infected by biological pathogens, and they cannot transmit diseases, and they are therefore also typically not on sick leave, and do not suffer, of course, from reduced productivity in the long run due to consequences of a certain sickness. Now, all of this should basically imply that if a pandemic hits, then this should raise the incentives to automate production, to substitute humans who are susceptible to transmissible diseases by robots who are not susceptible to transmissible diseases. What we do in this paper is to first set up a theory that addresses the decision to employ workers versus robots in the face of a pandemic, and then test the theoretical implications by Austrian employment data before and after the emergence of COVID-19. Let's start with the theoretical background, and here we assume that in an economy there are firms that produce a certain consumption good, which we denote by YT, that all the households buy and consume. And these firms produce this good by the use of physical capital in the form of the assembly line, and the tasks that have to be performed along the assembly line denoted by xt omega. So omega are the different tasks, and we have j different tasks to be performed along the assembly line. So in principle, this conforms very well to the Cobb-Douglas production function and this modeling of the production process as we see it here in this picture, where we have the different production steps, the different tasks that have to be applied on this assembly line. And then we have alpha, the parameter of the production function, that is the elasticity of output with respect to input of task omega, and that's just a standard parameter. Now we know that there will be an inverse demand function for the specific tasks, and that's basically if there is a profit maximizing firm, it maximizes its profits by choosing certain inputs, assembly lines and tasks. And for the optimal task input, we would have the derivative of this profit function with respect to the task omega. And if we take this derivative, we see alpha comes down from the exponent. The exponent is reduced by -1, and the sum drops out because the task omega only appears in one term of this sum. So this is the inverse demand function, or what would be, if this was traded on the market, the price that a task producer can actually charge for a task. Now what we assume is that tasks are supplied according to this production function that we have here, and these tasks could be supplied in-house, for example. But a crucial point here is now that the tasks can either be performed by workers, LT omega, with a productivity ATL omega, so that's the productivity of workers in performing the task omega, or by robots that we denote by P for programmable labor here, and they have a productivity for this particular task of ATP omega. And then we have diminishing returns, so beta is a parameter that is smaller than 1. Now the crucial point here is from a technological perspective, humans and robots are perfect substitutes here. But whether it pays off for the firm to employ a human or a robot depends, of course, on the productivity, on the relative productivity of humans in performing the tasks versus robots. And the crucial point here is that the productivity of humans depends on the infection risk at work. So if infection risk at work is higher, their productivity will be lower. Now the crucial point is that this production function allows for the situation that we have here, where humans are substituted by robots, so we do not produce with humans but with robots. That would be the case if the productivity of robots in performing a certain task omega is particularly high. Then the firm would choose to employ robots and not workers, because that would lead to a higher profit. Now we want to determine optimal employment of humans, of workers, for those tasks that are performed by humans, and optimal employment of robots for the tasks that are performed by robots. So we assume that task suppliers, that could be in-house, now maximize their profits. And what are their profits? Well, that's the revenue. The revenue is the price that I can charge for a task that I supply. So that's from the inverse demand function on the previous slide, multiplied by the amount of tasks I supply. So that would be the revenue I collect with supplying task omega. And I have to subtract the costs. If I produce with workers, then the wage bill that I have to pay is the wage rate, the going wage rate for workers multiplied by the number of workers I employ. And if instead I use robots to produce the task, then I would have to multiply the cost of robots by the amount of robots that I employ. And the cost of robots, that is how much physical capital I need to produce one robot, that we denote by gamma, and the interest rate, because that's the opportunity cost of capital. So that would be the cost of production if I choose to produce with robots. Now we just plug into this profit function the inverse demand function from the previous slide for the price here, and the production function here we plug in for xt omega, and we get the profit function in this form. Now we know that profit maximization implies that the derivative of the profit function with respect to the input of the corresponding production factor has to be equal to 0. So for those tasks that are produced by human workers, the derivative of the profit function with respect to employment has to be equal to 0. And for those tasks that are produced by robots, the derivative of the profit function with respect to robot input has to be equal to 0. So we can take the derivative of the profit function with respect to LT and with respect to PT to get these two expressions. And from these two expressions, we can isolate optimal employment of workers for the tasks that are produced by humans and optimal robot use for the tasks that are produced by robots. These resulting expressions have a very intuitive interpretation. What we see here is that the exponent is negative because alpha and beta are both smaller than 1, between 0 and 1 both. So that means the product is between 0 and 1. And if we subtract 1 here, the exponent here becomes negative. That implies that if the term in square brackets increases, this reduces the left-hand side, so employment here. And we see this immediately. If wages go up, then employment would go down. And that's intuitive. If firms face higher labor costs, they would reduce employment. And a similar story holds true for robots. So if the cost of robots increases, then the firms that produce the tasks that are produced by robots would reduce robot use, basically. By contrast, if there are more assembly lines in the firms, ceteris paribus, they would use more workers and more robots, basically, because they have to staff more assembly lines. What's a little bit more difficult to interpret is the effect of productivity, because there are two forces that work against each other. So on the one hand, if productivity of one of these production factors increases, so ATL omega for workers or ATP omega for robots, that would mean that you can produce a certain output level with a lower production factor input. So you could save on your input, basically. On the other hand, for the firm, it becomes more profitable to use more of the production input factor because the production input factor has become more productive. And therefore, one effect of this AT here, so this is a positive effect on employment, and this AT has a negative effect on employment here, and the same holds true for robot use. However, what is clear is that the effect, the positive effect dominates. So if productivity increases, a firm would indeed employ more of the corresponding production factor. And again, all of these effects are kind of quite intuitive. So what we can do now is to plug back optimal employment into the profit function for the tasks that are produced by workers. So we get profits of the tasks produced by workers of firms that supply these tasks. And we do the same for robots. So now we get the profits for tasks produced with human workers and profits with respect to tasks produced by robots. And then we can sort the tasks according actually to the effective cost of production with the two different production factors. So that would be the cost of producing a unit of output by workers and the cost of producing 1 unit of output by robots. And there will be certain tasks for which robot production is much, much more efficient and cost effective, and some other tasks for which production by humans is more cost effective. And somewhere in between, there will be a task, if we sort this in ascending order, where it would be exactly indifferent. So where the profit of the task producer is the same, irrespective of whether it chooses to employ humans or robots. So, and that's a cut-off level that we can determine explicitly. How is it determined? Well, we set the two profit functions equal to each other and then solve actually for the ratio of productivities between workers and robots on the left-hand side and the costs of production on the right-hand side. So what we get is basically the left-hand side is the productivity ratio between workers and robots, and the right-hand side is the cost ratio between workers and robots. And the higher the productivity ratio, the more likely it would be that the task is performed by workers, and the lower the productivity ratio, the more likely is that it is performed by robots. That means that a sorting of tasks will occur, where the tasks for which the ratio of labor productivity divided by robot productivity is higher than the ratio of costs for human production by robot production, these tasks will be performed by workers. So there, using workers leads to a higher profit level than using robots. And the opposite holds true if the ratio of productivity of workers by robots is lower than the cost ratio. So these tasks would be performed by robots. Now, the crucial point is that if a pandemic occurs, the infection risk at work shifts upwards, and this reduces the productivity of workers who are susceptible to infections, but not of robots who are not susceptible to infections. And that means kind of the cut-off level of the tasks changes so that more tasks would be performed by robots and fewer tasks would be performed by humans at the margin. And now this basically implies that we would see fewer workers in the production process and more robots. This is an effect that happens on the margin. So those workers who are susceptible to automation, and if their infection risk increases, then they would be substituted by robots. If a certain task cannot be substituted by robots whatsoever, then of course also this change in productivity due to a change in the infection risk would not make such a difference. So only workers who are susceptible to automation would be affected by this increase in the infection risk at work. So from these theoretical considerations, actually three testable hypotheses emerge. The first one is that an increase in automation risk would reduce employment ceteris paribus. That's clear because if the risk of automation is higher, if a task can be performed by robots better, then this would reduce human employment ceteris paribus. Second, the COVID-19 has a pandemic has an effect on the employment of workers. So it has a negative effect on the employment of workers, but only on those that exhibit a high automation risk. And the COVID-19 pandemic has no effect on the employment for workers that exhibit a low automation risk. That comes basically from what I've talked about on the previous slide. So the infection risk at work only has an impact on employment for workers that are susceptible to automation. Now we want to test these hypotheses. So how do we do that? We set up a regression equation where we have employment on the left-hand side in a particular occupation, and we also can differentiate in the occupations between gender, skills, so education basically, age of the worker, the region, the industry, and of course we have time t. Now we regress this employment differentiated according all these characteristics on the viral transmission risk in a certain occupation. So that's the infection risk at work basically. Then on a dummy variable for the COVID-19 pandemic, then on the routine task intensity of this particular occupation, which measures how well this occupation can be automated, basically, based on the tasks that the workers in this occupation have to perform. And we have an interaction term between the viral transmission risk and the COVID-19 pandemic. And then we control for gender, skills, age, industry, region, and occupation fixed effects, basically. And we have the error term here. So what our hypothesis would now imply is that hypothesis 1, that automation risk reduces employment, would mean that beta 3 is smaller than 0. Hypothesis 2, that the COVID-19 pandemic has a negative effect on employment for workers, that would be that beta 4, this interaction term between the viral transmission risk and the COVID-19 pandemic, that this parameter estimate is smaller than 0, so that this is significantly negative. However, only for automatable jobs. For non-automatable jobs, we should not see an effect, which is our third hypothesis. So our hypothesis 3 is that beta 4 is equal to 0 for non-automatable jobs. Now, with respect to the data, we use data from 2015 to 2021. We have yearly data from the Austrian Microcensus, so the Mikrozensus Arbeitskräfteerhebung from Statistik Austria, on employment in the different occupations, and on hours worked, the work volume, and on the kind of controls that we have: age, gender, education, and industry, region, occupation, where we will introduce fixed effects. The viral transmission risk is constructed for Austria based on the findings of Chernoff and Worman 2023. So we translate their findings to the Austrian labor market. And we do a similar exercise for the routine task intensity that is constructed for Austria based on the work by Autor and co-authors who construct this routine task index. Now, what do we find? Here, these are our central findings, the COVID-related labor market outcomes, where we have two sets of estimates. The first set of estimates, in the first set of estimates, we have employment as the dependent variable. And in the second set of estimates, we have the work volume as the dependent variable. Now I first only look at the results with respect to employment. What we see here is we have three different columns, one where we put all occupations together, and then we split the sample into non-automatable occupations and automatable occupations according to some threshold levels in the routine task intensity. Now, what we observe here is that the routine task intensity has a negative effect on employment for automatable jobs, but not for non-automatable jobs, of course. The viral transmission risk actually has a positive association with employment. Now, this may seem surprising at first because the viral transmission risk kind of should reduce productivity. However, this captures structural change here because it's those occupations where there is a lot of personal interaction that are in services and that have received a lot of job growth over the last years. And that's picked up here by this coefficient. But the coefficient that we are actually interested in is the interaction between the viral transmission risk and the dummy variable for the COVID-19 pandemic. And what we see here is indeed our hypothesis 2, that we have a reduction in employment for those workers that are automatable when the COVID-19 pandemic strikes and they have high viral transmission risk. So the interaction term between viral transmission risk and the COVID-19 pandemic is positive, but only for automatable workers, not for non-automatable workers. Here it's insignificant. And that's perfectly in line with our hypotheses 2 and 3. In all of these specifications, we have the control variables and industry fixed effects, occupation fixed effects, and region fixed effects. Now, however, there is one aspect in the German labor market that may be important in the context of the COVID-19 pandemic, and that's the policy response that we had in the form of furlough schemes, the so-called Kurzarbeit in Austria, where people could reduce their employment even to 0%, so they could stay at home and still be fully paid and not being counted as unemployed due to state subsidies, basically. So in this case, of course, the people would be registered as employed, but they would not work. Fortunately, we have data on work volume as well, so we can run the same regressions on work volume instead of employment. And according to this policy, what we would expect to see is stronger effects on the work volume, because for this person who sits at home, who is not counted as unemployed, but the work volume is counted as zero. So we should observe a stronger effect of all what we have said so far in this case of the work volume being the dependent variable. And indeed, that's what we observe. So we observe here this coefficient is larger in absolute size, but this is not the really interesting one. Interesting is the interaction term here, and we see this interaction term between the viral transmission risk and the COVID-19 pandemic is twice the size, actually, the coefficient estimate, and it's significant at the 1% level here for the work volume and only at the 5% level here for employment. So all these results support our hypotheses 1, 2, and 3, and particularly we also see that these furlough schemes in Austria have had their intended effects, so they would reduce unemployment basically, but work volume is reduced, and that the effects are strengthened in our case. That gives credence that indeed the mechanism behind the results is the one that we described in the theoretical part, because if this is the case, we would expect to see, due to the policy of the furlough scheme in Austria, stronger effects on work volume than employment. Now we can also illustrate these effects to some extent, where we plot here employment levels in Austria from 2015 yearly to 2021. And we construct four groups of employees. The ones with a high routine task intensity and a high viral transmission risk. So these are the workers who are susceptible to automation and to viral transmission risk at the workplace. Then we have the opposite group that has a low routine task intensity and a low viral transmission risk. So they are not that susceptible to automation and not that do not face such a high risk of getting infected. And then we have two groups in between. One has a high routine task intensity and a low viral transmission risk. So they are easy to substitute by robots, but do not face a high infection risk. And the opposite, those with a low routine task intensity and with a high infection risk. And now let's just look at the two extreme cases. The first one is this group of occupations that are not susceptible to a high automation risk and not susceptible to a high viral transmission risk. That's this dashed line here. Now here, the COVID-19 pandemic, that's the last year before the COVID-19 pandemic, and we normalize the employment index here to 100. And what we see here is that employment increases for these occupations, and there is actually no change after COVID whatsoever. So we don't see any change in the trend of employment growth here for the workers that have a low viral transmission risk and a low automation risk. However, we see exactly we see something completely different for those workers that have a high automation risk and a high viral transmission risk. So that's the solid line here that goes up. So employment growth until 2019, and then there is a sharp drop, so an employment decrease. And that's even employment, not hours worked. So with hours worked, we could expect that this is even stronger. So therefore, I think we can conclude that automatability affects employment in the Austrian labor market, that the viral transmission risk also affects employment in the pandemic, but this effect is only visible for automatable jobs. Now the effects are stronger for work volume than for the level of employment, and this would hint in the direction that indeed Kurzarbeit schemes, furlough schemes in Austria have had the intended effects of reducing unemployment at the expense of just reducing working hours and keeping people in employment. Thank you very much for your attention.